Let's continue with example 2. Show that every positive even integer is of the form 2q and that of every positive odd integer is of the form 2q plus 1, where q is some integer. Let us show this by applying a division lemma. According to division lemma, what it says? For every two positive integers a and b, there exists two integers q and r such that the relation, satisfying the relation a is equal to b times q plus remainder r. You should understand q as the quotient, r as the remainder when a and b are divided. Okay. Now here r should be always lying between 0 and b. So lying between 0 and b means it can be taken 0 or greater than 0, but always less than b. It can't take exact value as b, but it should be less than b. So remember, this is the condition for r. Now by applying this division lemma for these any two integers, let a be any integer. For this, coming to this question, let a be any positive integer or any integer, and then let b be equal to 2. Let us take b is equal to 2. This 2 we are taking as b. Okay. So now by applying division lemma to this, the relation here, this type of relation, you can write it as a is equal to, here b is 2, right? So b times q, some quotient q plus remainder r. Okay, according to the division lemma, I am applying just b is equal to 2 in this place, and I wrote a is equal to 2q plus r. And you should understand that this r should be lying between, according to this condition, r should be lying between greater than or equal to 0 but less than 2. According to b is 2 here. So r should lie between 0 and 2. It can also take 0. So between 0 and 2 means what are the values r can take? R can take either 0 or r can take 1. Right? If r is equal to 0, let us take the two cases. If r is equal to 0, what happens? Then substitute that value. Here. A is equal to 2q only you will get, because 2q plus 0, which gives you a is equal to 2q. If a is equal to 2q, that means a is even here, because if you multiply any integer with 2, you will get definitely a as even. Now next case, if r is equal to 1, what happens? Then a is equal to, substitute that r is equal to 1 in this a is equal to. So a is equal to 2q plus 1, right? So then if you observe, if a is even here, if 2q is even, here you are thinking 2q as even, and then 2q plus 1. So always the two integers should be of the form either even or odd. So if 2q is even, the other integer, this should be odd. So our 2q plus 1 is an odd integer, So in that way you can prove this both by applying division lemma. Let us see the third example. The third example is, show that any positive odd integer is of the form 4q plus 1 and or 4q plus 3, where q is some integer. Show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. For example, according to division lemma, we know that for any integers a and b, there exist two integers q and r such that the relation a is equal to b times q plus r, right? So this is according to theorem 1.1, division lemma, Euclid's division lemma. So here q can be a positive integer where and r is always lying between 0 and b. 0 and b. It should be less than b, but it can be greater than or equal to 0. So this is according to theorem. So now let us come to this question. Here let us take a as any number, like a as in any integer, and let us take b as 4. Why I am taking b as 4? That comes from here. Let us, whatever number is here in the question, for this, in this place, that number you take as 4. Now that number you take as for b. Now coming to here, according to the relation a is equal to bq plus r, let us substitute the values. A is equal to b plus, I am substituting 4, 4q plus r. As I know, q is greater than or equal to 0 because it should be a positive integer, and r should be careful, r can take the values 0 less than or equal to r less than b here, actually b means our b is here 4. So r can take the values starts from 0 to less than 4, not 4, below 4. So it can take 0 also because equal to sign is there. R is greater than or equal to 0 and less than 4. So that means R can take the values 0, 1, 2 and only up to 3, not 4. Okay. So now let us take each case. What happens if R is equal to 0? If R is equal to 0, A is equal to 4q plus 0, which is 4q. Keep it aside. If r is equal to 1, what happens if r is equal to 1? A is equal to, put r plus 1, 4q plus 1. If r is equal to 2, if r is equal to 2, A is equal to 4q plus 2. If r is equal to 3, if r is equal to 3, A is equal to 4q plus 3. Right? Now what happens? If A is equal to 4q, it is divisible by 2. Definitely it is divisible by 2. That means it is even. 4q is even. Now what happens? 4q plus 2. This is also divisible by 2. So it is also even. So what do you understand? A is equal to 4q is even and A is equal to 4q plus 2 is also even. So the remaining two numbers, these two are positive odd integers. So A is equal to 4q plus 1. Add even number 1 to that. Here 4q is already even. You add 1 to that, you will get an odd integer. For any even integer, add 1. You will get definitely an odd. Similarly, here also 4q plus 2 is even with odd. So add 1 to that. 2 plus 1 gives you 3. So this is also an odd. So whatever even number is there, you add 1, you will get an odd integer. For every even integer, add 1, you will get an odd integer. So definitely A is equal to 4q plus 1 and A is equal to 4q plus 3. These two are compulsory positive odd integers. So hey, here comes the proof. Odd integers by proving according to Euclid's division lemma. Applying the Euclid's division lemma, we proved that A is equal to 4q plus 1 and A is equal to 4q plus 3. A is a odd integer, right? Let's go to next question. Now the example 4 is, a sweet seller has 420 kaju burfis and 130 badam burfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of that can be placed in each stack for this purpose? So for this can be done by calculating HCF of 420 and 130. Why we have to take 420 and 130 HCF? Because HCF of this 420 and 130 is the greatest number that divides them both exactly with 0 remainder. The greatest number that divides 420 and 130 is the HCF itself. That means this HCF gives you the maximum number of burfis that can be placed in each stack. Right? So that we get the least possible number of stacks used. And the area of the tray that used up will be the least. So we want HCF of 420 and 130. This can be done by using division algorithm. Okay, let us use the Euclid's division algorithm to find HCF of 420 and 130. So here 420 is greater than 130. So let us divide them 130 with 420. So 133s are 390. 13 are 39. So 133s would be 390. Let us subtract. You will get the remainder as 30. So here according to division lemma, you can write it as 420 is equal to, this is the step 1. As we discussed previously, this would be the step 1. 420 is equal to 130 times 3 plus the remainder 30. This will be the first step. Now coming to the next step. Divide again this 30 what remainder you got and 130. So 30 table, like think like 3 table. 3 4s are 12. So 30 4s would be 120. The 10 is the remainder. Now write step 2 using that. Step 2 comes to 130 is equal to this 130. This 130 is equal to 30 times 4 plus remainder 10. Right? Next, let us divide continuously until we get 0 remainder. Let us take this 10 as divisor now and previous divisor as dividend. Continue the division. 10 3 is 30. Simple. So we got 0 remainder. Now at what stage you get 0 as a remainder? At that stage whatever is the divisor, that would be our HCF. So let us write step 3 now. Step 3 would be 30 is equal to 10 times 3 plus 0. Now HCF is the 10. HCF of, I'll write HCF of 420 and 130 is equal to 10. That means the sweet seller can make stacks of 10. The sweet seller can make stacks of 10. So that the least number of possible stacks she can make and the area would be also smaller. Okay. So let us continue with exercise, next exercise in the next video.